Hi everybody, today we are going to be learning a new derivative rule called the product rule. I apologize, my voice isn't 100% today. I think it's good enough that you'll be able to understand me, hopefully. Okay, so now that we're really into derivatives, we're going to start learning a lot of different derivative rules. And they get quite complex. So complex that we have to kind of spend a lot of our mental energy actually applying the rule. And so often we forget about what a derivative actually is. So if hopefully I remember when you come into class every day, I'm going to say, what is a derivative? The derivative is just the slope of the tangent, okay? So it's a way to represent instantaneous rate of change in a function. So what is the product rule? Why do we need the product rule? Well, there's all different kinds of functions out there, tons of different kinds of functions. And some of them, a lot of sophisticated ones, happen to be the product of two functions. So we want to have a way to find the derivative without having to actually FOIL out and make some humongously long polynomial and use what we already know. We want to have a new rule so we can do things more efficiently. So if you kind of look through your note, you can see the kind of functions we're going to be differentiating, like this one here. Okay, if we had to expand this out, we could, but we don't really want to, etc. Like you can see down here, something to the power 6. Yeah, we do not want to have to expand that, or something even with a root. There is a way of doing it where we don't have to actually use what we did before. So that is what the product rule is all about. So we're going to verify what the product rule is. We're going to prove why it is what it is. That's what I mean there. And then we're going to use it to actually find the derivative of products. So let's think about what you might think the product rule is going to be. So taking a look at this, we might think, well, Mrs. Weeks, you just take the derivative of this, which is 2x, and then you take the derivative of this, which is 1, and you multiply them together. So the derivative is 2x. That's it. Unfortunately, that's not what it is. It's not quite that simple. So we are going to actually show through this example that the derivative is not just the derivative of one times the derivative of the other. So if we call this part p at x, and we call this part q at x, then p prime at x, its derivative is just 2x plus 0, so just 2x, and then q prime at x is just 1, right, plus 0. So therefore, p prime at x, q prime at x is just 2x times 1, which is 2x. Okay, so I'm going to show you that this is not actually true. So think about how I can do that. How am I going to show that? Well, I'm going to FOIL this and then take the derivative, and you'll see that it's not the same thing. So if I FOIL, I get x squared times x, which is x to the power 3, and then 5x squared, and then 2x plus 10. Okay, and so if I take the derivative of this, you can clearly see it's 3x squared plus 10x plus 2. So not at all like this. So we can conclude quite confidently that f prime at x is not equal to q prime at x times p prime at x. Sorry, I should have done p and then q. So if that's not the derivative, then what is? Well, if we have two functions multiplied together, then the derivative is the derivative of the first one times just the normal second one. So not the derivative, just the normal second, plus the normal first times the derivative of the second. Okay, so if u and v are functions of x, then the derivative of u times v is du dx times v, dv dx times u. So this means the derivative of u, and then just keep v normal, and the derivative of v, just keep u normal. Okay, so notice these are in different orders than the first question. That's just because addition is commutative, it doesn't matter. And then here, my kind of like cheater way of thinking about it is if you have first times second, then the derivative is the derivative of the first times the second plus the first times the derivative of the second. So we get to prove this now. Woo -woo. So we're going to prove this using limits, and we're going to use a little trickaroo that's a little bit confusing, but don't freak out. I wouldn't expect you to develop this on your own in grade 12. At this point, I just expect that you understand what is actually happening. So we're going to take, oops, almost forgot my limit. Mrs. Weeds. Okay. So it's the limit. So what is the derivative? Let's go back to first principles. So the limit as h approaches 0 of p at x plus h, q at x plus h, minus p at x, q at x. Okay. So remember, this is just the definition. This is just using the divided by h, the difference quotient. Okay, so now we're going to do a little trick where we're going to add and subtract the same thing within the limit statement. So I'll put it in a different color so you can really see what's going on. So we're still going to have p at x plus h, q at x plus h. But now I'm just going to throw some in the middle. And I can do this because I'm adding and subtracting the same thing, which essentially means 0. So I'm going to subtract p at x, q at x plus h, and I'm going to also add p at x, q at x plus h. Okay, and then we are going to subtract p at x, q at x as before. So sorry, that's multiplied together. And this whole big shebang is over h. Okay, so now I am going to common factor out. I'm just going to put the equal sign over here so I have more room. From these first two terms, see what they have in common. They both have the q at x plus h in common. So I'm going to common factor that out, but I'm going to put that common factor second. So I'm going to write p at x plus h minus p at x first, and then q at x plus h. Okay, so again, I looked at these first two terms, and I just common factored out a q at x plus h. I just put that part after, so then this is what happens when you common factor that out. And then on the second part, so now I'm looking at these two terms, you can see that p at x is common. So again, I'm going to common factor that out, but put it in the end as well. So you get q at x plus h minus q at x, and then you get a p at x left over. Okay, and this is again still all over h. So we get the limit as h approaches 0. Okay, so now why is this exciting, you're wondering? Well, based on our limit rules, I can separate this into a whole bunch of limits now. So this is p at x plus h minus p at x over h, and then times the limit as h approaches 0 of q at x plus h, plus the limit as h approaches 0 of q at x plus h minus q at x over h, times the limit, oh, I'm running out of room, as h approaches 0 of p at x. P at x. That's a p at x. Okay, so there we go. Excuse me. So now look what happens. Okay, if you go to this limit and you just let this h go to 0, you just get q to x. So this whole statement is the same thing as writing the derivative of p at x. This is the definition by first principles of p at x, and this turns into just q at x. And then this plus this is just the definition of q prime at x. And this, you're just left with p at x because there is no h even involved in that statement. So there you go. That's the proof. Isn't that super fun? So this shows that this above statement is actually true. All right, so now let's go and do what you've all been waiting for, actually use the product rule. Okay, so the derivative here. Okay, so we have this first and we have this second. Okay, it says find the slope of the tangent at 1. So let's find the derivative first, and then we will find the derivative at 1. So you take the derivative of the first term. So you bring down the 3, so you get 15x squared. Bring down the 2 plus 14x, and then plus 0. So you just leave it there. And then you keep the second one the exact same as it used to be. Okay, so that's the first bit. And then you add, now I keep the first one the exact same. And now I take the derivative of the second one, so 4x plus 1. Okay, now notice that this question just asked for the slope of the tangent at a specific point. So it's up to you if you actually want to simplify this first or not. If I just asked you for the derivative, I would expect that you actually go through and simplify this. So FOIL and simplify. But I just asked you for the slope of the tangent at 1. So in that case, you could just sub in 1 into this gross thing if you want. Okay, or like I said, if I just asked you for the derivative, you are expected to simplify this. Okay, unless I say do not simplify. So if you put 1 into here, you get 15 plus 14 times 2 plus 1 plus 6 plus 5 plus 7 plus 3 times 4 plus 1. If you put that all into your calculator, do it right, you get 336. So that means when I have this function, the slope of the tangent at 1 is 336. Crazy huge slope, but that's what it is. So I want you guys to actually try this next simple one now. Pause the video, try f at x and g at x, okay? I'm going to give you the answers. I'll show you just the answer, but pause first and then unpause to check your answers. So now pause. Okay, so you should have gotten for this as the final answer 6x plus 13. And you should have gotten for this as the final answer 48x cubed minus 15x squared plus 4x plus 1. So hopefully you got those right. Okay, so now we're moving on to the extended product rule. So this is if you actually have a product of more than just 2 functions. Okay, so basically, if you have 3 functions multiplied together, then the derivative is the derivative of the first, normal, normal, plus the derivative, plus normal, sorry, first derivative of the second, normal, 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 derivative of the third. So you have 3 expressions that you're adding together, and in each one, you take the derivative of a different one and keep the other 2 the same. Okay, so for example, I'll do a simple example here. You have x squared times x plus 3 times x to the power 5. Okay, so these are 3 functions multiplied together. The derivative, it's long. Okay, so you take the derivative of the first guy, so 2x, x plus 3, and then keep the other 2 the same. Okay, so that's a clump, and then now you add new clump. So the first one stays the same. Now you're taking the derivative of this. New clump. Clump, it's a very technical math term. Okay, now the derivative of the last guy. Okay, so that's the extended product rule if there's more than two functions being multiplied. So now we have the power of a function rule for integers. So this is when, if you look at this example below, you basically have a function to the power, to one power, okay? So what we are tempted to do here is just bring the n down and then subtract 1, just like we would for polynomials, but that's not quite what we have to do here. So I'm going to do just a short little proof of this. So think about this. Another way of writing this is g to the x times g to the x times g to the x, etc., and you multiply it together n times. Okay, that's what that exponent n means. It means you take g at x and you multiply it together n times. So if we were actually to write the derivative, we would put, I'm going to do a different color. Actually, that n times, you might want to write above it or to the side because it's going to get in my way there. So I'm just going to erase it. Okay, so a derivative, then you would take the derivative of the first and then, multiply all the other normal guys together until you get to the last one. Okay, and then that's the first chunk. Clump. Did I say clump before or chunk? I think clump. So now you add. Now the first one stays normal. The second one gets differentiated. The third one stays normal all the way to the end. Okay? And you would keep doing this until you get to the last group where everyone's normal. I should put 3 there since I haven't. ... until the last one is differentiated. So check this out. How many times are you doing this? Okay, that's what you got to think about. So there's this clump, this clump, this clump. How many clumps are there going to be? Well, there's going to be n of this. Okay, so each clump, I'm going to call it, I've never used that word before. I don't know why it came into my head, but that's what I'm using. Each clump has 1 g prime at x and n minus 1 g at x's, right? Because each clump has n things multiplied together. One of them is the derivative, and then the rest of them, so n minus 1 of them are just normal g at x's. And so then there are n clumps. Very technical. So we can write this as n. Okay, we have n g at x to the n minus 1s, and then 1 g prime at x. Okay, so the derivative of this is we bring down the n, we reduce this by 1, but then we have to multiply by the derivative of what's inside here. So in Leibniz notation, if you have d times u to the n in terms of dx, then you get n times u to the n minus 1 times du dx. So you have to take the derivative of that inner function. Okay, or this might help. Here's my weird Mrs. Lean's way. So if you have blah to the power n, then y prime is n. Keep blah the same, n minus 1, but then you got to multiply it by blah prime, so the derivative of that. All right, so let's actually do this. Okay, keep that above there. So let's find this derivative. Okay, so we bring down the 6. We keep the bracket the same. This is what's crucial. Okay, you do not differentiate the bracket yet. Okay, that's the same as up there. And we reduce this exponent by 1, and then we multiply it by just the derivative of what's in the bracket. Okay, so you bring down the n, 6. You leave what's inside the bracket the same. You reduce this by 1, and then you multiply by the derivative of what's inside. Okay, so now we're going to put that rule together with the product rule. It's going to get really fun. So you have to look at this as two functions, okay? This is our first function, and this is our second function. Okay, you really need to stay focused on that point. So this is function 1, and this is function 2. So the first thing we're going to do is take the derivative of function 1. So the derivative of function 1 has this rule with the exponent, okay? It's actually called the chain rule. We learn it as the chain rule later. So it has this, what did I call it up there? This power of a function rule, because it's a function that's being taken to a power. So when we take the derivative of that, we have to consider that. So we bring down the 4. We're left with 3x minus 1. We keep it the same. Now we take down the exponent by 1, and then multiply by the derivative of what's inside, which is just 3. Okay, so that whole thing, what I just did, is the derivative of function 1. Okay, now remember, we have to now, because it's a product rule, multiply that by just this normal function. So this is just function 2. All right, and now remember, we add just normal, sorry, down here, add just normal function 1. Okay. Times the derivative of function 2. Okay. So first and foremost, we think about this as a function times a function, but then when we take the derivative of this special type of function, we have to remember the rules that go along with it. Okay, I have 2 more examples, and they just show little tricks that we still have with what we learned, and then there's a couple practice questions for you there. So tomorrow, or in the next video, whatever that is, you will actually learn what's called the quotient rule, which will tell you how to deal with stuff like this. But you can still actually deal with this using the product rule. And understanding how to do that will help you when we actually prove the quotient rule tomorrow. So you can rewrite this as a product of 2x plus 5 times 3x minus 1 to the negative 1, okay? So you can take that denominator to the power of negative 1, excuse me, which is the same thing as dividing it. Okay, so now when we take the derivative, y prime, we take the derivative of the first guy, so 2, times normal second guy, plus normal first guy. Okay, now times derivative of this guy. So let's be careful. So we bring down the negative 1. We keep the 3x minus 1 the same. We make this negative 2. Remember, you're subtracting 1. And then we have to multiply by the derivative of the inside. Okay, so this whole thing here is the derivative of that second function. So now we are able to reduce with our magical powers of understanding algebra, right? So this is 2 over 3x minus 1 plus, now be careful, okay? Watch what I'm going to do here. Actually, I'm going to subtract, not plus. Why am I subtracting? Think about it. Because I have this minus 1 here. So minus, so I'm going to put the 2x plus 5 and the 3 together, and I'm going to put this all in brackets. So you get 6x plus 15 over bracket 3x minus 1 all squared. Okay, that's what that negative 2 means. So now we can actually get a common denominator of 3x minus 1 all squared. So you have to multiply this 2 times the 3x minus 1, okay, minus 6x minus 15, distribute the negative, and that's all over 3x minus 1 all squared. So when you expand this out and simplify, you actually just get negative 17 over 3x minus 1 all squared. So this is what I mean, we get lost in what we're actually doing. So this is the derivative of this function. So this represents the slope of the tangent at any given point to this rational function. Okay, last example. Find the equation of the normal to this function at x equals 4. So I actually graphed this on GeoGebra for you. So this is the function here, f of x equals root 2x plus 1. So it's a square root function. And they want to look at specifically at the point here at 4. So remember, they want a normal. So a normal is a straight line that cuts it at a 90-degree angle that is perpendicular to the curve at that point. So what we're going to do is find the slope of this tangent. So this is the tangent to the curve at x equals 4. You can see here it has a slope of 1/3. We're going to actually find that. And then the normal will be this line here. This is the answer, but I'm going to show you how to get there. That is actually perpendicular right at 4 to this curve. Okay, so that's what it means to find the normal. My voice is really going now, I apologize. Okay, so first thing we have to do is rewrite this function as 2x plus 1 to the power 1/2 so that we can find the derivative. Okay, so f prime at x, we take down the 1/2, we leave the bracket the same, we reduce our exponent by 1, and we take the derivative of this inside function. So the 1/2 times the 2 is 1, and the negative 1/2 is 1 over, square root of 2x plus 1. So f prime at 4 is, okay, we put in 4 here, we get 2 times 4 is 8, 8 plus 1. So we get 1 over root 9, which is 1/3. Okay, so this is the slope of the tangent. So that's a 3, if you can't tell. This is the slope of the tangent at 4. So that equals the slope. So let's go up here. So therefore, the slope of the perpendicular line will be -3, right? The negative reciprocal. Okay. We also need to find the point 4. We need to find what f at 4 is to put that into the function to be able to find the y-intercept. And you can find that that is just 3. If you put 4 into this function, you get 3. So then I set up my y equals mx plus b, and I sub in my y, my m, my x, solve for b. So you get 3 equals -3 times 4 plus b. So we get b is equal to 15. So then my final answer is y is equal to -3x plus 15. So again, that is the equation of the normal, which that's the equation of this purplish line. You can see I wrote it here. So that is the equation of the line perpendicular to the curve at that point. All right, so now you just have a couple different practice questions. Okay, here you have this chain rule or power of a function rule to practice, and here you have something like the example on the last page where you have a product of 2 functions, but one of the functions has that special rule. So you guys try that, and I will take it up tomorrow in class. Make sure you got the right answer. Make sure you guys ask me, I might forget. All right, so just remember, product rule, the reason why we learn it is because that's how we find the derivative of functions where it's the product of 2 functions. It's just the slope of the tangent. It's just rate of change. Thanks for watching, guys. Hope you learned more.